In this video, I want to talk about why is viscous dissipation important and why do I even mention it. So viscous dissipation, what is viscous dissipation? Well, viscous dissipation represents the conversion of mechanical energy such as pressure, velocity, or elevation difference into internal energy due to the fluid's friction. So what happens is you might have pressure changes or velocity changes or potential energy changes, and all of these are considered mechanical energies. So if you have any changes in these parameters, what happens is usually they're being changed due to some friction. So let's say if you're in a pipe, you have friction in the walls of the pipe as the fluid is traveling inside the pipe, and this friction essentially eats up the mechanical energy available in the system. And the resulting friction is heat. So that heat that is being produced by the conversion of mechanical energy is absorbed back by the fluid as the internal energy of the fluid rises. So you can see that, if you touch a pipe, you can realize that the pipe is hot. And it's hot because all of the friction losses that is occurring because of all of the bends in the friction of the pipe is causing the mechanical energy of the fluid to actually be consumed and destructed into heat losses. And that heat losses is then being absorbed by the fluid as sensible energy. And if you remember, I said sensible energy is part of internal energy. So you have then the internal energy of the system going up, and therefore you'll actually feel it because the temperature of the system goes up. So this process increases the internal energy of the fluid and can result in a temperature rise. In the simplified energy balance, we assume negligible viscous dissipation. And so this means there's no significant conversion of mechanical energy into internal energy. Now, if viscous dissipation is significant, this means that mechanical energy losses must be accounted for. And so these losses increase the fluid's internal energy and are reflected in the change in enthalpy between the inlet and the outlet. And so in such cases, the simplified relationship of Q equals mCpΔT is no longer sufficient to describe the heat transfer alone. And the full energy balance using the enthalpies must be applied. So then the heat exchange, you have to use this equation, which is the original equation, which is the heat exchange is equal to the mass flow rate multiplied by delta H, which is the difference between the enthalpy of the fluid coming in and the enthalpy of the fluid leaving the system. Now, what I really want to show you here, which I'm super excited about, even though this is a heat transfer course, but because we're talking about energy balances, I want to show you how in fluid mechanics they derive their pump equation using the same open system energy balance that we use in our heat transfer applications and also in our thermodynamic applications. Because one of the things that I find often is because you have different courses in university. So you have a fluid mechanics course that just teaches you about, for instance, pump sizing. And so you don't get a chance to appreciate or realize that the energy equation that you're using in this class comes from the same place of the energy equation that you're using perhaps in your thermodynamics or heat transfer class. So I'm hoping to take a moment now so that we can take a step back and be able to see that this energy balance equation is universal. And from it, then you could apply some assumptions and reach to these energy balance equations that you're used to using. So let's look at this